Okay. Okay. Good afternoon and welcome to the non-associative algebra community. I'm glad to introduce the speaker of today, Professor František Marko from the Pennsylvania State University. The title of his talk is Blocks of Rational Supermodules over some quasi-reductive supergroups in positive characteristics. Please.
Thank you very much for the introduction, and thank you for giving me the opportunity to speak to this community. I'm not quite sure that I'm fitting exactly in the middle of the interest of most of the participants, but I hope that you are going to find this interesting. I'm going to talk about one part of the work that I have done throughout the years with Alexandr Zubkov, who is originally from Omsk State Pedagogical University. Right now, he is the United Arab Emirates University. And we have undertaken a project to describe blocks of some quasi-reductive supergroups in positive characteristics. The positive characteristic is the main topic here, because many of the results were already known in characteristic 0, but it's much harder and much more complicated, and it requires different methods for positive characteristic. What we were going through, we were looking at the general linear supergroup, we were looking at the ortho-symplectic supergroup, a periplectic supergroup, and queer supergroup. So I will talk about these four examples. I'm aware that Professor Zubkov also was doing some work on exceptional supergroups, but I'm not going to touch on that today. I will spend probably the bigger part of the talk talking about describing the situation of a general linear supergroup, and then I will touch on the other three cases. The last case of the queer supergroup is still a work under progress. So let me start. And the first, I would like to describe what are supergroups and what are blocks. Many of you probably know that, but in case you don't, let me go very briefly over these topics. So we will consider the ground field of characteristic 0, or more importantly, of characteristic P that is bigger than 2. We are disregarding characteristic P equals 2 because we are thinking about supergroups. In that case, it's not going to bring anything new. So as is known, a supergroup is a functor from category of commutative K superalgebra to the category of groups that is represented by Hopf superalgebra that is finitely generated. And then you have supermodules are really supercomodules over this Hopf superalgebra. Then we have a parity switch functor that will be denoted by pi, that is just switching even and odd components. And as in the classical case, you can just define extensions as a right-derived functors of the home functor. So this is of course well known. So let me just go faster through this part. All right, it's a little bit glitchy. So to get into the notion of the block, you are interested in finding out which two simple modules will have non-trivial extensions. And since we are dealing with the supergroup, we are asking whether there is an extension between simple modules or perhaps between the simple module and the parity shift of the simple modules. So we would like to look at those, and equivalence classes under this relationship will be called blocks. And the main purpose of our interest is describing the blocks. And then, of course, you can have you have the split over the extension functors, as you can see there. I'm not going to go there, but the first part, sometimes a necessary condition for the pair of irreducible supermodules to belong to the same block is called the linkage principle. A linkage principle is something that does not completely describe blocks, but it gives you like half of the problem. So you would know then when the two simples are not in the same block, and this is usually accomplished by applying action of an element from a center of the distribution algebra, superalgebra. So really, that is a partial information about blocks, but you do not get a complete description of blocks. And we were really trying to get a complete description of blocks, as was in the classical case. So let me briefly go over the definition of the general linear supergroup. If I'm boring you with this, I apologize. So we start with a generic matrix that is split into 4 blocks. As you can see, x0, 0, 0, 1, 1, 0, x1, 1. The diagonal blocks will be even, the off-diagonal blocks will be odd, and the entries in these matrices are called even or odd. And then you can form a polynomial superalgebra on these generators xij, and then you will get the Hopf algebra, superalgebra structure on this by the following co-multiplication and co-multiplication delta. And then you will have the augmentation map epsilon as well. So this is analogous to the classical situation for the general linear group, except that we need to really keep track of parity of some, and we will have, in this case, we have a supercommutativity relation. Of course, if you have 2 elements, they supercommute, meaning that they commute unless both of them are odd, in which case you will have a minus sign over there. So that's the general linear supergroup. And of course, then you have the usual concepts like the maximal torus T, characters, weights, which is set dominant whenever there are inequalities. Now, you have in this case, you have 2 sets of roots. I mean, you have blocks. You have the first block of size m and another block size n. And we really need to break the weights into 2 components. So the first component of the length m, you will have the dominance relationship bigger or equal for the elements of the first part. And then there is a break and there is no connection. And the second part, m+1 to m+n, are again related by the inequalities. And of course, this is related to the action of the while group on GLM and GLN. That is going to permute the elements, and therefore we can assign these inequalities. The root system for the general linear group is epsilon I minus epsilon j and plus or minus that when I is less than j, and it splits into positive, negative. And what else we have here? We have a parity function, and we have a bilinear form on this epsilon I, epsilon j that depends on parity. So this is really trying in complete analogy to the classical situation. So we have a torus, we have the characters, root systems, and the bilinear form. Next thing that we will consider obviously are Borel subgroups, Borel supergroups. All right, so let's see. And the irreducible supermodules. For the Borel subgroup, we will take one consisting of lower triangular matrices, because we can consider the other Borel subgroups, but let's take this one. And the important object in all of our studies are induced supermodules. So in this case, we are just inducing from the Borel super subgroup from the natural one-dimensional supermodule of weight lambda, and we are inducing it to the whole general linear supergroup GLMN. And the main point is really to understand the structure of these induced modules. In the classical case, understanding of the structure of induced modules will give you a strong linkage principle and a description of blocks. The situation is somehow analogous to in a super case that once you understand the simple compositional factors of induced supermodules, then you can describe the blocks. But before we go there, first question that comes into mind: when is this induced supermodule non-trivial, which means non-zero? And this is if and only if it is dominant. And you have the analogous results as in the classical case, that the Sokol is an irreducible supermodule of high-level lambda, and you have a correspondence between irreducible supermodules and this dominant weights lambda as described before. So now, once we have all of this terminology, now we will denote the simple modules by L lambda, and we will say that that simplest L lambda LMU are linked if and only if the the weights are linked. And so we would like to understand completely when the two simple modules are linked. So that's the task that was in front of us. What is interesting? Let me actually stop sharing, and I will come back to this. The main tool for understanding the structure of the induced module, I will share a different screen here. Is the following. Let me see. Right. If I can see this, this is my whiteboard. All right, I thought that I had something here, but since I don't have, I can write it down. So what is an important thing here is the following. Okay, I do not know why I'm writing in blue, but that's all right. We will do it. So if you take the induced modules over the even supergroup. So this is like classical induced module, and you can tensor it with a symmetric superalgebra over this component 1, 2 of the matrices. Then you will end up with an isomorphism. So this will be, as a superspace, this is going to be isomorphic to the induced modules over the whole supergroup G. So this is an observation. The isomorphism is only as a superspaces, but yet this allows us to kind of work inside of the induced module. And since the structure of the induced module of the linear group is known, then we can use this and we can work using super derivations and describe the structure of the induced module there. So this was one of the important ingredients of what we were doing there. I'm just going to stop sharing and I will come back to my original screen. Let's see, here it is. All right. All right. So now I would like to formulate some kind of a description of these blocks. And of course, as usual, for the classical case, we have a rho that is defined as half the sum of all of the positive roots. In the super case, we will have half the sum of the difference between the sum of positive roots of that are even and minus the sum of the positive roots that are odd. And we will say that the two weights are even linked if they are linked in the category of even GLM and GL cross GLN modules. So this is completely classical, and so we have an even linkage. And since the product of GLM and GLM is sitting inside of the general linear supergroup, so we have this even linkage. And it's easy to see that if you have two weights even linked, then there will be linked inside of the supergroup as well. So we will have one type of linkage, which is classical even, and then we will have an odd linkage, and we will say that the two weights are simply odd linked if there is an odd root that is positive, such that mu differs from lambda by either adding or subtracting alpha. This is that odd root, and P divides the value of the bilinear form of lambda plus rho and alpha. This can be described in a, we actually work in a different way, but it's the best way to simplest way to describe it for the purposes of this talk is just using the bilinear form that is in there. So if the characteristic P divides the value of this bilinear form, then the weights lambda and lambda plus or minus alpha will be linked. And actually we showed that indeed there is an extension of these two simple modules is non-trivial. So we have even linkage and we have this, which we call the simple odd linkage. And if you combine them together, so if you form a chain of weights such that either step in the chain is given by even linkage or the simple odd linkage, you will get a complete description of the block. So that's a result about the general linear supergroup, right? So it's not only a linkage principle, but it's a complete description of the block. Let me pause here for a second and see if there are any questions so far, because I'm just going to move to a different supergroup after this part. All right. So I don't see or hear any questions, so we can move on to the next topic. Okay, I'm sorry. So there is a historical remark that the description of blocks of a characteristic 0 was obtained by Serganova Gruson in 2010, and of a field of positive characteristic, there was a weak version of linkage that was proven by Kuyava, but it turns out that the descriptions given in a paper of Kuyava is not sufficient for the description of block. So it is a linkage principle, but not quite the description of the blocks. And there is some discussion here that I'm not going to go over, but I mean just that we indeed improve that. So our description of the blocks in a positive characteristic was the complete description. It was given first in that paper. All right. Let's move on then to the ortho-symplectic supergroups. The situation with ortho-symplectic supergroups is kind of much more difficult, and the way we approach this problem. So again, the task is how can we get the description of blocks of ortho-symplectic supergroups? I will show you a description, the complete description of blocks later, but it's not quite satisfactory. I mean, it's kind of technical. Yes, it is a description of blocks, but it doesn't give you that nice feeling that we had for the general linear supergroup. What is the method that we use? I mean, let me first talk about the method. To get this, to get the results about the block, we use the approach of Doty, that uses the Frobenius thickening and various morphism between Frobenius thickening. And basically, this principle of Doty gives us a way how to describe blocks if we can manage if we can understand the structure of induced modules over Frobenius thickenings and certain morphism between them. So we apply that, and for that reason, we really needed to look at the smallest possible example. And this, of course, it is going to be SPO21. So we have completely, we basically by hand, starting from a scratch, we analyze the structure for SP21 as the simplest example, and we describe the blocks for that one. So maybe I can just show you that, because the situation in general is quite messy. So I'm just going to show you what is the situation for the SPO21. Let me see. SPO21, I will find it here. Blocks. No. I mean, just I'm having a hard time finding it in a list of available options here. Just a second. All right. Up. And this would be all right. All right. You should be able to see it. So if you look down towards the end of the page. So here is a description of the blocks for the SPO21 supermodules. And there are going to be P blocks, and the description is rather nice. So it depends only on some congruence classes of modulo 2P. And this means, I mean, either L is congruent to K or L is congruent to 2P minus 1 minus K modulo 2P. So that way, I mean, this is nice description. So you have a good understanding of what are the blocks in the category of SPO21. All right. Now let me go to the general case. So, like in a classical case, if you understand that what is the structure over SL2, then of course you can work the general situation. All right. Let me go back. All right. Let me go back to the presentation. So let's talk about the ortho-symplectic supergroups. What we have here, I mean, what you can read here is the character group corresponding the bilinear form. It is a sub-supergroup that preserves a certain non-degenerate even symmetric supersymmetric bilinear form. I will not go into details. What you can see here next is what is the root system of the ortho-symplectic supergroup, and it depends whether M is even or odd, and then you can see exactly the description of the root system there, positive and a negative part as well. So of course it's a little bit problematic that you have to break it into these two cases, but all right. The description of dominant weight is kind of tricky already. That is a problem. So we will have two parts. There is a part of lambdas corresponding to 2n, and then the situation is reasonable. I mean, you have lambda 1 bigger or equal than lambda 2 up to bigger or equal to lambda n, and then you have a second part corresponding to m, and you have similar inequalities, but the condition, kind of very strange condition, that is tying up lambda n with the rest of the following roots, that is involves some number of p-removable cells in the Young diagram of the partition of mu. And again, I have no desire to go much deeper into this. So the thing is that even the description of irreducible supermodules that is given by these, and the results I'm quoting here is in a book of Xu and Wang, is tricky. So it's not straightforward. I mean, just if you are looking at the general situation. So we have irreducible modules that are indexed by weights corresponding to these properties, as you can see them here. Maybe I should probably be using the laser pointer, right? So these are the properties that are kind of non-trivial properties, because there is a number of p-removable cells in the Young diagrams that are indexed. All right. Here is the statement of the linkage for the ortho-symplectic supergroup. It's kind of difficult to understand, but at least we will see what is involved in there. So let's look at this. We will have the notion of simply isotropically odd linkage. And this is kind of similar to what we have seen for the general linear supergroup. So the characteristic of the field divides the bilinear form of lambda plus rho and alpha. This is exactly the same condition. And you will have the mu is lambda plus or minus alpha. So this is it is identical condition to what we have seen in the case of the general linear supergroup. But in addition to this, so this is the case when you have isotropic root. And when you have non-isotropic root, then alpha, then there is a different type of linkage that is given here. So if you have an odd non-isotropic positive root alpha and some integer r, the relationship between mu and lambda is that they differ by a multiple of alpha, and that multiple is kind of described in a really cumbersome way. L is the smallest non-negative residue of this value of the bilinear form minus 1/2 modulo power of p to the r. You can see here this is what we are getting because we were using the Frobenius thickening. So therefore we have to go to higher powers of p. And so L is described simply by computing the residue of some expression modulo p to the r. And there is another item here, which is L prime. And L prime is either L minus 1 or it is a weight that is given very explicitly, but I am not going to write it down here. It is a weight or subcomposition factor of the induced SPO2R supermodule of weight L. So as I mentioned, we understand this SPO2-1 rather well, and therefore we can describe the composition factors. And there is an explicit description in the paper. I'm not going to write it down. So the L prime is described, and then you have, this is a rather complicated non-isotropical odd linkage that is involved in there through, not in a case of isotropical odd linkage, it's just lambda plus or minus alpha. Here we have to take lambda minus some multiple of alpha. So it's not just alpha itself. And then when we have this, then the statement is that the two dominant weights belong to the same block if there is a sequence such that each element of the sequence is either simply isotrophically odd, which means this part, lambda, mu is lambda plus or minus alpha, or simply isotrophically. So there are three types. So it's a simply isotrophically odd link, simply non-isotrophically odd link, and there is an even linkage as well. So you have a combination of three types of linkage, and then you will get a description of the block. But again, it's technical. Yes, it is a complete description, but not very satisfying. All right. Any questions about this ortho-symplectic supergroup? To understand the structure of induced modules, it's every induced modules of this SPO21 is given like the almost two parallel string of SL2 modules. So we were looking at the SL2 module structure, and we were able somehow using characters and other methods, we were able to find out the structure of induced modules. And that's how we were able to do this, using the method of Doty, Frobenius kernels, an explicit description of the induced supermodules for the simplest possible case, SPO21. All right. So we have two more to go. Okay, so the results about the general linear supergroups were published more than 10 years ago. The results about the ortho-symplectic supergroup were published, I would guess, probably like 5 years ago. Results about the periplectic supergroup were submitted to archives this year. So this is a recent result. And finally, the results about the queer supergroups, they were not even submitted, but I mean, we already have some partial results. So we had a complete description of blocks for periplectic supergroups. What is interesting about the periplectic supergroup that it is the only of these four cases when the center of the universal enveloping algebra or center of the district is trivial. You don't have any non-trivial central elements. And indeed, in this case, because you don't have any non-trivial central elements, you are going to find out that there is a small number of blocks. And there is a small number of blocks in a characteristic 0, and there is a small number of blocks in positive characteristic as well. And as you can expect, the number of blocks in positive characteristic is smaller than the number of blocks in the characteristic 0. I would like to give us some important observations about the periplectic super subgroup. Again, I'm not even defining it, but let's look at the root system. And there is a positive part R plus and R minus. And what I would like to point out that this system is not symmetric, unlike in the previous cases. For example, if you look here, K equals L will give you a root 2 epsilon k. And that doesn't have a counterpart in R plus. So there is a root in R minus that is that minus 2 epsilon k is not there. So it's the asymmetry of the root system that is the biggest driver. And actually, we exploit this asymmetry of the root system extensively, and we were able to find out the description of blocks. And this was even done earlier in characteristic 0. I mean, maybe not in such an explicit form that basically the root system asymmetry is giving you the linkage. First, okay, so the weight is dominant if and only if lambda 1 is bigger than lambda 2 and so on. And every irreducible supermodule is uniquely defined by up to the parity shift by highest dominant weight. So here we have a good understanding of labeling of irreducible supermodules, unlike in the case of ortho-symplectic group. I can talk more about this is the main idea of how we manage to describe the blocks. So the asymmetry of the root system brings in the asymmetry of the good filtration of induced supermodules, and there is more information about this here. So you have a natural grading on supermodules by the length, and we are looking at the supermodules as as modules over the even supergroup. And then it breaks down into a lot of weight spaces corresponding to that action. And so the smallest non-zero degree component is the length of, if you take the simple supermodule, you will have the weight is L, and this is the smallest non-zero component. The largest non-zero degree component is L plus 2R. And even a description of what this R exactly is not so easy. But we are going to say that, so we have the weight lambda, which is a dominant weight. And then we will corresponding to lambda, we assign the highest anti-dominant weight of this largest degree L plus 2R, we denote it by L plus. So we have a dominant weight lambda on one side, and then inside of the same simple module, you will have lambda plus, which is the highest anti-dominant weight, like that. And we are working on these two concepts. All right. So what you can do, looking at these different components considered over the even subgroup, you will have the degree component, and you look at it as a GLN module, and it will have a good filtration. And we can describe the filtrations. They are described here very explicitly. And of course, this is Littlewood, Richardson, or the Pierre rules, or the rules, if you want. This is well known, the classical situation description of the good filtration of these induced modules. And then, so this is a second degree component, because the first degree is just easy, and the last degree is just easy. So we are moving closer, and we are looking at the second degree components of the weight L plus 2 or L plus R minus 2. And we are using the good filtration and describing what these are. So we have an understanding of how the second degree and the second to last component degree component works. And then we apply the duality. So there is a duality that will move the induced modules over the Borel subgroup of B minus to the Borel subgroup B plus. And what you're going to find out that there are certain components that are matching, and there are simple modules that they do not have a counterpart. So there is an asymmetry of these induced for these induced supermodules, and there is a weight on one side that is not on the other side, and the vice versa. And this is really the essence that is going to allow us to get the description of the blocks, because of this asymmetry. So here are the results. In a characteristic 0, it was determined by this is a paper of many people in 2019, that there are n+1 different blocks of PN supermodules up to the parity shift. So what we did here, that in characteristic P, which is this is a paper submitted on arXiv already. So there are up to the parity shift only 2 blocks. And of course, they are represented by the weight 0, trivial weight 0 and 0, 0, 0 up to -1. So it's kind of surprising that it does not depend on n. So, and it doesn't depend on a characteristic at all. And the fact that there are so few blocks, as I said, in characteristic 0, is because there are no non-trivial elements of the center of the universal developing algebra there. And we were able to get only like two different blocks in positive characteristics. And one of the other tools that we were using was the description that was given in a PhD thesis of Janssen that characterize induced GLN modules that are irreducible in characteristic P. And this is perhaps, this interest is this, the result is perhaps of, I mean, it may be interesting just to look at that result if I will be able to get there. All right, so let me look at here it is. All right, I'm over on space, but I will move to the statement of the characterization of Janssen of irreducible modules in characteristic P. And okay, here it is. So I will just make it bigger. Here is the statement that is due to Janssen. Again,
But
this is interesting.
excuse me, we cannot
wasn't
see
aware.
the paper. You should share.
You
We
cannot you cannot see the paper
No.
because it says to me you are sharing this. Okay, so I will stop sharing it. I will try it again because the message that I got is that that I'm sharing it. So let me do it again.
Okay.
Can you see it
okay.
now? All right.
Yeah,
Great.
yeah.
Great. Because I mean, okay. All right. So this is an interesting statement on its own. So you have this is about general linear group, not supergroup. So you will have a while modules for the general linear group. And the statement is that such a while module in characteristic P is irreducible if and only if the following conditions are satisfied. Now let's look at this. So you will look at the difference of the weight components minus, and what you need to produce in order for the module to be irreducible. You need to produce intermediate weights in such a way that every time that you move from the next step, you are just moving by the power of P. So here, and the complete statement is here. So if you can find a sequence of indices such that these quantities are powers of P, then the while module is irreducible. If you cannot do it, then it is reducible. And to me, this is a very interesting statement on its own. And for us, it was an important tool because we were able to establish some kind of a partial linkage under the assumption that some while module was irreducible. And then this criteria is really telling us, well, you can recognize when the Y module is irreducible. And then we were moving through a chain of irreducible modules through this partial linkage until we got where we needed to go. So we were able to tie up almost, I mean, there are 2 blocks up to the parity shift. And there must be at least 2 blocks, which is natural. And then essentially what it says here that you pick any two ways that could be linked, and they are linked, and you go there through a partial linkage that we established. And this is a fundamental criteria that we will use for our work there. And it was kind of amusing to just find it that this is Janssen's PhD result. This is at the end of his PhD thesis. All right. Any questions about this? Because this is probably all I'm going to say about the periplectic supergroup. All right. So I will just stop sharing this, and I will go back to my presentation. All right. So this is where I was. So we have this. So we have a very surprising result that you have 4 blocks, no matter what P is, no matter what N is. And so as I said, this is a recent result, and the final example are queer supergroups. I will not go too much into the details, but essentially the queer supergroup is a supergroup that has inside like GLN, and you have like even copy of GLN and odd copy of GLN essentially. So what is known about blocks of QN? Sergeyev found certain central elements in a distribution algebra in the universal and developing algebra of the corresponding Lie supergroup, and Brandan and Kleshev established the linkage principle in a modular case, essentially saying that if some quantity, which is called the content, is identical for the weights, I mean, if the content is different, they cannot be linked. So this is a linkage principle. Of course, this is only one part of the description of the blocks. I will actually show you exactly what is this statement, that content of the weight, which is it's also kind of interesting. So what we did, as in the previous cases, the starting point is to understand the simplest possible supergroup of the given type. So in this case, it's Q2. So in Q2, we have computed the induced supermodules, and this was a really tremendous computation. It has more than 100 pages. But nevertheless, we managed to compute the induced supermodules, and we were able to find out that that we basically proved the converse implication, that if the two weights have the same content, then they are linked. So the Brundtland and Klescher proved that if they have different content, they couldn't be linked. And now, at least for Q2, we are able to show that the same contents means linkage. And our idea is to use the same methods of Doty using Frobenius thickening to describe blocks in the general case, so that we would need to describe now situations over Frobenius kernels and some morphisms. It's going to be a lot of work, but I mean, that's what we are working on right now. What I would like to show you is how this linkage principle of Brundtland and Klescher. So how can you recognize, again, I will share it with a different file. How do you recognize, I need to give you, okay, I will need to scroll down in this preprint. I hope that you can see it now, but I will, okay, I will show you the statement. Oh, I'm sorry, I'm sorry, this is a wrong paper, that's periplectic. I need to show you the queer paper. Just a second. Okay. All right. If can you see that paper now? All right.
Not yet.
Not yet. All right. The message says that I'm screen sharing. If you cannot see it, I will do it again. I will stop sharing and I will do it again.
Okay, yeah, it's better.
So there is some technical glitch, or maybe there is a delay in that. Can you see now the screen?
Unfortunately, not.
Okay, again, it tells me that I'm sharing it. Well,
maybe,
all right.
Maybe you should first open the file and then share it before.
Yes.
Yes, it says me that I'm sharing it already.
But maybe it's on the other screen. Maybe it's something else. Do you have two screens or only one?
Yes. Let me see. Let me open it. I have that. It's open. Let's see if I can share it. If not, this is not a big deal, but I would like to show it if possible. But if not, then let's try it again.
Okay.
It's okay.
Yes.
Now you can see it. All right.
Yes.
Yes.
So it's more complicated statement, but in the case of Q2, this is what is the linkage principle of Brundtland and Klescher. They are saying that the two weights are linked if their content is the same, and the content is obtained the following way. You count the number of expressions that are of the form lambda I plus 1 squared minus lambda I plus 1. And so the residue modulo P is R, and you count how many of those you have. And then you do the same thing with lambda I instead. So you lined up how many of those are there. And then the content is the difference between these two. So the problem is that you might have an offsetting pieces. So you might have the part from AR that will be offset with BR. And but this is combinatorially very easy to do. I actually wrote a small program when I was looking at this. You can compute the content quickly, now the statement is if you have the same content, then they are linked. But in a sense, it's a little bit misleading, this statement. It's the action of the central element of the universal enveloping algebra cannot distinguish this lambda and mu. You do not know if the extension between simples is not trivial, but you can see that it's like, you know, it's so you have one way, and this is a rather easy combinatorial description of that. And so what we did, we managed to actually compute the converse, saying that, well, if, let me go back to the presentation. So we were able to actually see that indeed those weights that are indistinguishable by Sergeyev element are indeed linked. In a sense, there is a sequence of extensions of simple modules that will go from lambda to mu. So as I said, this is a work in progress. So we made the first important step on analyzing the Q2. So at least we understand what's going on there, and now we will look at the Frobenius thickening, and hopefully we will be able to establish the description of blocks for the queer superalgebra. And so here are some of my references, and this would conclude my talk, and I will be happy to answer questions.
Okay, thank you very much for your interesting talk. Are there any questions? Comments? Remarks?
I understand that this is not in the mainstream of your interest, but I think it's some of the results are interesting.
Yeah. Okay, if there are no questions, let's thank the speaker again.
Thank you.
And we will resume on next Monday at the usual time. Thanks again. Bye-bye.
Thank you. Bye-bye.